दुनिया हजबी करना लगन सही है चाहे तो so let's take examples yesterday we were taking so we had this example okay so we are considering there was an error yesterday one point I said wrong okay there is no error one point I said wrong okay so that I will clarify here so what we are considering will be two spin half particles or two level systems okay got it so here the point what I said was wrong yesterday so I am considering two spin half particles I will consider only the spin degree of freedom the Hilbert space that is covered by these 2 degrees of freedom clear and the rest of the wave function I am not considering that means let's say if you are having an electron in the hydrogen atom it carries spin as well as the spin part clear okay so I will not consider the special part of the wave function I will simply restrict to myself to where this spin part clear so I will then say effectively these two particles are two level systems clear so you are having one spin half particle as a two level system another spin half particle as another two level system clear so our system is here what at two level systems clear got it okay so what will be the Hilbert space dimension here the dimension of the vector space yesterday I told you it is 4 okay 2 corresponds to one particle and 2 corresponds to the another particle so in that case I am having a 4-dimensional space if I consider the special part as well so the dimensionality will increase so in okay so I am considering the dimensionality of the Hilbert space only with respect to this spin degree of freedom clear got it so remember this very point okay now tell me what were the states okay so I denote let's say this plus so let me put this plus what this is actually so eigenstate of the Sz operator clear so Sz in the plus direction what is this minus so it is Sz along the negative direction clear so these are the eigenstates okay so let me write it plus minus these are the eigenstates of this Sz operator clear so that means each spin half particle will be described by the state plus or minus got it okay so how many particles okay so I can consider now let's write our vector space okay possible number of states okay so let's write what are the possible states so for two particles so I will be having plus for particle 1 okay a tensor product a plus for particle 2 so these are labels just to identify it the first corresponds to the particle 1 and second corresponds to what particle 2 clear okay so you can okay so the matrix representation you can also write it is as 1 0 and this is as 0 1 okay so this is a general theme now let's go to our let's construct the basis or the number of possible states what we can have okay so another will be a particle 1 can be in the plus 1 state and a particle 2 can be in the minus state and similarly I will be having a particle 1 in minus and particle 2 in plus and I can be having minus and minus clear so this represents our okay 4-dimensional vector space clear so all these 4 are linearly independent of each other clear 4 possibilities 4 linearly independent vectors are there clear समझ आओ okay so this describes our 4-dimensional vector space that means the vector space the dimensionality of the vector space for two level systems is how much 4 now if you are having n two level systems so what will be the dimensionality dimensionality will be dimensionality of the vector space will be 2 raised power n. Clear? So if I consider n particles, okay, So, okay, so you can write it in, let's put it in the matrix fashion. So, what it will be? So, let's write this plus 1 tensor plus 2. Okay, so how it look like? This plus. So, what is plus? 1 0. Clear? So, it is 1 0. Okay, tensor. What is plus? 1 0. Now, what is, how we define the tensor product? Yesterday I told you, take this one first element and multiply the entire matrix. So that means this 1 1 0 and this 0 1 0. Clear? So how much is that? So 1 0 0 0. So this is your one vector. Right? Clear? Okay, so similarly you can write this thing. So this is now a vector in this very space. Okay, so now you are having this plus 1 tensor minus 2. So if you write it, so it is 1 0. Okay, tensor 0 1 2. So what it will be? 1 multiplied by 0 0, 1 multiplied by 1 1, 0 0 and 0. So like this. Okay, clear? Similarly, you can show this thing minus 1 tensor plus 2. So this we can show as 0 0 1 0, and you can show this minus 1 tensor minus 2 as 0 0 0 1. Clear? So this is actually, this is the matrix representation of these vectors. Now you see, so your okay, so this vector space is a 4-dimensional with these kinds of vectors. Like we write E1 as 1 0 0 0, E2 as 0 1 0 0. If I write it in this fashion, 0 0 1 0. So E4 as 0 0 0 1. So this will represent your what? 4-dimensional vector space having the basis set as E1, E2, E3, E4. Clear? Okay, we will not use that notation. We will be sticking to this kind of notation. Clear? Got it? Okay. Okay, so now, okay, so this is a basis set. Now I can construct an arbitrary state out of a basis set. So I can represent an arbitrary two particle state as a superposition of all these basis states. Clear? Okay, so let's write it. Okay. So let's write, okay, a general two particle state. Okay, can be written two, okay, two particle state. Okay, so of two state of particles. Okay, so you measure yourself. So I am considering only in terms of the spin space. So I will write this psi for this composite system. So as, let's say, alpha 1, this plus. Okay, so I will simplify this notation instead of writing this like this way. So I will write, okay, so let me simplify notation. Let's simplify notation. Okay, so I am having, let's say, vector Vi, okay, tensor vector Wj, let's say. Clear? So this corresponds to particle 1, this corresponds to, so this I can write as Vi tensor Wj. It is understood first belongs to particle 1, second belongs to particle 2. Okay, so you can compactify it like this. Vi then comma Wj. Got it? To remove this tensor notation. Got it? So it means it's a two particle state. So much of with Vi belongs to the state of the particle 1, Wj belongs to the state of particle 2. Clear? So to remove this tensor, because we will be having large numbers of these tensors here. Clear? So much of? Okay. So what I will write then? Okay, so I will write like this plus, then I will write this plus. Clear? So the first plus corresponding to particle 1, second corresponds to particle 2. Then I will write alpha 2 plus minus, then I will write alpha 3 minus plus, then I will write as alpha 4 minus. Clear? Okay, got it? So what is the normalization? So if it is a normalized objective, then mod of alpha 1 square plus mod of alpha 2 square plus mod of alpha 3 square plus mod of alpha 4 square is equal to 1. So you can write this in a compacted notation like this. You can write this psi 1 2 is equal to summation of, let's say, ij. Let me write alpha ij, okay, vi, okay, then say wg, okay. So sure, where I goes, I is plus minus, j is plus minus, so that it will be v plus and okay, v plus minus, w plus minus. समझ आओ? Got it? Okay, so instead of because I used alpha here, I will put as a here. Clear? Got it? Everybody? Okay, so what will be? Let's take I is equal to plus, j is equal to plus. It will be a plus plus, v plus, w plus. Clear? So I will call v plus as plus and w plus as plus. Clear? समझ आओ? Everybody? Or okay, so if it is a problem for you, so I will write it as an I, j. Okay, I j is equal to plus minus. Clear? समझ आओ? Okay, so now what will be the alpha 1? It will be a plus plus. Alpha 2 will be a plus minus. Alpha 3 will be okay, and so on. Got it? Okay. So now, so this is how we constructed general states out of these two states. Similarly, okay, so let's say if you are having 3 particles, okay, let's say you are having 3 6.5 particles. What would be the basis state? First, you construct actually a basis state. Okay, so let's take the 3 state, then you can generalize it to the more states. Okay. 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 So let's say you are having 3 6.5 particles. Clear? So what are the possibilities? Now tell me. Now tell me what are the possibilities. Okay, so you are having actually for okay plus minus, okay, plus minus, okay, plus minus for the 3 particles. Clear? So let's put all the possible combinations. So what is your basis set? So it is like this in plus, okay, plus plus, then plus minus. Oh sorry, you have having 3. Okay, so you are having 3 possible 3 vectors. So plus, plus, and plus. Clear? Then you are having plus, plus, minus. Then plus, minus, plus. Then minus, plus, plus. Clear? Then okay, plus, minus, minus. Then minus, plus, minus. Okay. Then you are having minus, minus, plus. Got it? Okay, then you are having minus, minus, minus. Okay, so how many states are there? 8 possible states. That's what, so dimensionality of the vector space is what? So it is 8. So that's actually 2 raised for 3. Got it? Okay, so now you can construct an arbitrary state. Okay, so arbitrary state will be what? So let's write for 3 particles, an arbitrary state you can put, let's say, summation over I, j, k, they go as plus minus. So let's say alpha I, j, k, okay, I tensor, j tensor, okay, got it? So this is how you can construct a general 3, okay, 3 particle state, okay, in the spin basis. Got it? समझ आओ? So now let's construct the operators. Okay. So let's look how we can act operators on these states. Clear? So let's try to figure out. So in the 2 particle case, so our first example is what? 2 particle. So what are our states? So plus plus, plus minus, minus plus, and minus minus. Okay, so now, okay, so tell me, what is the total angular momentum of this very state? So let me, okay, so let's ask this way. So how I can calculate the total spin angular momentum of these states? Got it? समझ रहे हो? So, okay, what I am saying, I have two spin half particles. What are the possible values of spin? So you add, okay, half half to half minus half. Clear? So what are the possible values? 1, 1 and 0. Clear? Is it? So the total spin will be what? 1 or 0. समझ रहे हो? Okay, what are the z components? It can be 1, 0, minus 1 and 0. Because you are having 4 states. Okay. So you are having like this half plus half to half minus half. This is how you calculate the angular momentum. So what will be the total angular momentum? So Sz total will be what? Either 1 or 0. So now let's, sorry, S total. S total. So let's write Sz total. What it will be? For this one, it will be minus 1, 0, 1. So for this, it will be 0. Is this the case? So you are having these three cases. Now let's figure out which state is having S equal to 1. This total spin equal to 1. It is this very state. Because both spins are up. Clear? So what about the value here? 0. One is up, another is down. So that means the vectors are opposite to each other. So it is 0. Total spin is what? 0. What is the total spin here? 0. So what is this total spin here? Minus 1. So how many you have got? All the possible states. Clear? So now this is just looking at these kind of values. But I want to operate at Sz operate, sorry, S total operate on these various states and figure out what is the value of the spin. Clear? So what I mean by that, so I want, okay, like this. Let's say you are having a total spin operator. Okay? So it acts on this plus state. Clear? So what is our total spin operator? So it is actually the sum of two spin operators. Okay? So it's like this thing. Okay, so we need to figure out all these things. So first I will construct what is our ST. So you write ST is actually the sum of what? The spin operator of the first particle, then spin operator of the second operator or particle. Clear? Okay, but in our, okay, so this is how you write the sum of two operators. Clear? But in our notation, because I want S1 to act on the Hilbert space of the particle 1 and S2 in the Hilbert space of particle 2. So I will write our own notation, what we have developed yesterday. Clear? So what is that? So I can write this thing as ST like this. S1 acting on the particle 1 and keeping particle 2 as such. Okay? Like this thing. Then you are having, okay, S2 acting on particle 2, keeping particle 1 as such. Clear? So there is no problem now. Got it? समझ आओ? So I will tell you what is the problem in this notation in a moment when we look at the matrix representation of this operator. Clear? समझ आओ? Okay, so this is much more, I mean, good notation than this kind of thing. Clear? Okay, so now let's act on this. You'll understand it in a moment. Okay? Okay. So let's take this S plus acting on this plus. So what is actually this thing? So what is ST? So it is actually S1, okay, I2 plus. So I2 cancel S2. Clear? So what is this plus? It's actually plus 1, okay, cancel. Got it? समझ आओ? समझ आओ? Okay. So now let's operate these things. Now operate. So what it means? So it's like this thing. So S1. Okay. So I will skip one step. Right. So this S1 will act on this plus, and I2 will act on this thing in the second Hilbert space like this thing. Plus 1 cancel I2 keeping this as such. Okay, so then you are having I2, it will act on this thing. So it's a lengthy notation, but It's correct. Okay. Sorry, this is I1. Yes. Clear? So you are having two terms. Got it? So now what S1 is yielding me? No, I should not operate S because S does not operate directly. I should operate SZ. Clear? So I should operate SZ because you cannot operate. You have to operate S square. समझ आवा? So can you operate S directly? Can you operate S directly? What are the eigenvalues of S? Okay, what are the eigenvalues of L? Okay, eigenvalues, yes. How? Those are actually the eigenvalues of L square. So you have to operate L square and LZ. Okay? Or you have to operate S square or SZ. So I will operate SZ total. So we will figure out the Z component. Clear? समझ आवा? But for the values of S, okay, so all these states, this state, okay, this state, they will be having S actually 1, total spin is 1. Okay? Huh? So we will be having 3 states which are having total spin equal to 1. Total spin. The Z component can be 0 or 1 or minus 1. Clear? So, समझ आवा? Okay, so I will show it in a moment. So it means I need to look at the total this Z component. समझ आवा? हाँ समझ. So you should have stopped with here. Oh, you see Clear? So here you should have understood. You cannot operate S directly on plus because there are no eigenstates for S or okay. So why? What is the reason? The reason being S does not commute with SZ. And what we have constructed the basis, it is the SZ basis. Is it? These are actually all the eigenstates of SZ. You sure? Yes, okay, good. So what is, okay, when SZ will act on this plus, what it will give me? H cross by 2. Clear? So it will give me simply H cross by 2. 1 will act on this thing, it will keep it as such. Okay? Then, okay, you are having plus and plus. Now SZ will act on plus, it will give me H cross by 2. Clear? So I will write it as plus H cross by 2 plus 1 tensor plus 2. I have taken the common then, this very vector. What you have got now? So it is H cross plus 1 tensor plus 2, or you can write H cross plus 1. Got it? Now what is the, okay, so SZ value of this thing? What is the SZ value of this thing? What is the value? H cross. So H cross is the unit, okay? So what it is actually? Plus 1. Tisha? So what is the SZ value? Plus 1. Okay? समझ आवा? Okay. So let's take this plus and minus. Okay? Let's take now this SZ total acts on this plus and minus. Clear? So समझ आवा? Okay. So it's actually plus 1 tensor minus 2. Clear? So it is plus 1 minus like this thing. Got it? Okay, so now let's write it. So what SZ gives me? It is H cross by 2 plus 1 tensor minus 2. Got it? Then this SZ acting on this minus will give me minus H cross by 2. So it's minus H cross by 2 plus 1 tensor minus. So what are they? Same. What you are getting? S0. So I can put like this thing, 0 times plus 1 tensor minus 2. So it is 0 times plus minus. Got it? So what is the eigenvalue for this state? 0. 0. Is it? So SZ total is what? 0. So similarly, if you take minus and plus, okay? So समझ आया? So if everybody has written it? So if you take now this SZ total acting on this thing, so as Z total acting on this minus plus, so it will give 0 minus plus. Clear? Now let's write this as Z total acting on this minus and minus. Now when first S Z will act on minus, okay, so this minus, it will give you minus H cross by 2. And in the second term, it will also give you minus H cross by 2. So it is minus H cross, minus. Clear? So this is how you can figure out. Let's say I am giving an arbitrary state and I want you to figure out what is the Z component of that very state. Total spin, Z component of the total spin of that very state. What you will do? You will simply operate as operator as the total on that very state. You will get actually it is eigenvalue. Okay, if it is the eigenstate. Clear? Now let's take a general state and figure out what. Okay. Okay, so let me take the general state. So I require these things. So these values are there. So I am having as Z total acting on this plus plus. So it gives me H cross plus plus. Okay, then you are having as Z total acting on plus minus. It gives me 0 plus minus. If you are having as Z total acting on minus plus, it gives you 0 minus plus. I am keeping this as such. Okay, you can put 0. Huh? So I am saying, so this is actually these are actually the eigenstates of this as Z total. Huh? So similarly, you are having as the total minus minus, it is minus H cross minus and minus. Clear? Got it? Okay, so now let's take the general state. So I am having my general state psi 1, 2. Okay? So let's take what that is. Alpha 1 plus plus. Okay, alpha 2 plus minus. Okay, plus alpha 3 minus plus. Okay, plus alpha 4 minus. Got it? Now let's apply SZ total on it. So now you should got actually how we operate these operators on these various states. Clear? Any problem? If you have any more if you have any confusion, just tell me. Eh? Any confusion?
No, sir.
Okay, good. So it is called the split. Okay? So let's operate this SZ total on this very state. You are having alpha 1 SZ total acting on this plus plus. So alpha, okay, so if you don't know these values, just do the same way what we have done. Eh? Okay, so I'll be simply using the values here. Eh? Yes? Okay, alpha 2 SZ total acting on plus minus, plus alpha 3 SZ total acting on minus plus, plus alpha 4 SZ total acting on minus minus. Okay, so now tell me what is the value here as a total? It gives me H cross. So this gives you 0. Okay, so this again what? 0. Now look here. So you get actually H cross. So in that case you get minus H cross. So I will take H cross out. So what you are having? Minus alpha 4 minus minus. So what does it mean? So you are having here psi 1, 2. You don't have psi here. Is it? So it means this psi 1, 2, this general state is not the eigenstate of what? SZ total. Clear? समझ आओ? Okay, now if I want to construct it to be the eigenstate. Okay? So let's, okay, so what are the possible eigenvalues here? 1 or 0. So समझ ना? Sorry. 1, 0, minus 1 and 0. So you are having 4 values for SZ total in this case. And I want to construct out of this psi 1, 2 the most general states which are having what? What I should have? Eigenvalues what? 1, 0, minus 1 and 0. Clear? So let's try to figure out. So if I, okay. So let's take one case. Okay. Okay, let's construct, okay, an eigenstate of, a general eigenstate I should say, eigenstate of SZ total having eigenvalue 0. What? Eigenvalue? Got it? So what I want? Eigenvalue to be 0. Clear? समझ एवं? Okay. So now what I need? So I know. So I have to operate this SZ on this general state. okay, and figure out what it gives me. So what I want? So actually I want this condition as a total acting on this psi1 2, it is equal to 0. Clear? समझ आया? So psi1 2 is a general state and I need to see how it looks like now. Clear? So now you know what as a total acts on the psi1 2, it gives you alpha 1 this thing and alpha 4 this thing. So it implies that alpha 1 has to be 0 and alpha 4 has to be 0. So it implies, okay, so let's call this as first term, okay. Therefore from first term, from equation first term, we must have what? Alpha 1 is equal to 0 is equal to alpha 4. Clear? So if I have, so then I can have SZ acting on this thing is equal to 0. Now let's look, when I put alpha 1 and alpha 4 equal to 0, so therefore our general state having SZ total is equal to 0, that means 0 spin angular moment, Z component of the spin angular momentum is what? Psi 1 2, okay. So what alpha 2? No. So let's take, so it is simply alpha 2 plus minus plus alpha 3 minus. So it is a linear combination of these. Okay, you know what is the value of SZ total in this very state? 0. What is the value of SZ total in this state? 0. So it is a linear combination of these two SZ total 0 states. Clear? Okay, so now there is, okay, so you can go, okay, so now what I do, I demand something different now on this very state. So I want to say you something about this very state. It is a very important state, what we are trying to construct. So let's say, okay, demand Sx total is also 0 on this very state. Okay? So what I am saying, so if I am having Sx total, that means total Sx component of the angular momentum, I want to act on this psi1 2 and it should yield me what? 0. Clear? So now let's try to apply this as the Sx total on this thing. So which implies if I am having now Sx total acting on this psi1 2, it will be like this thing. Sx1 tensor I2 plus, okay, I1 tensor Sx2. Okay, so it is acting on what? Alpha, okay, plus like this thing minus, then you are having alpha 3 minus 1 tensor. Everybody is following it? Okay. So now let's apply this Sx. So Sx will act on this plus and this, okay, I2 will act on this minus. So when Sx will act on plus, it gives you what? So plus is flipped to minus because Sx flips. Last time I told you. So look here. So you are having Sx is actually half of h cross by sigma x. Now apply Sx on, let's say, 1 0. So it means h cross by 2 sigma x means 0 1 1 0 acting on 1 0. How much is that? 0 1. Clear? So that means it flips. Plus is going to minus, minus is going to plus. Okay, so let's apply. So it will be alpha, okay, plus, so this will be actually h cross by 2 from here, okay, then you are having this, okay, alpha plus 1, okay, minus 2, okay, so it will be like this thing, sorry, it is alpha 1, alpha 1 or alpha 2, alpha 2, okay, so now apply this thing, so this Sx will flip this thing, so what you will get? Now this will be minus. So it will be h cross by 2. So plus will remain as such. This will become plus. Clear? Okay. So eigenvalues will be actually. So it will be h cross by 2 always here. So in the next case, you are having, so it is alpha 2 here. Then you are having alpha 3. It's again h cross by 2. It will become plus. This will become plus. Okay. Then you are having alpha 3. H cross by 2. So it will become minus, then some minus. Okay. So if you see, it's like this thing. These are two terms. Okay. H cross by 2 kind of thing. Alpha 2 plus alpha 3 plus 1. Okay. Plus 2 plus minus 1 tensor minus 2. So this is the result. Clear? So just arrange them. So this will be the result. Now what I want as a total to be 0. What it should be? So it implies therefore. So our demand implies. Okay. Our demand implies alpha 2 is equal to minus alpha 2. Now what you got there? Therefore your SI, which is having actually SZ total what? 0, and also what? SX total equal to 0. So how much is that? Now let's write that. So you take alpha 2, okay, here. So what remains there? It is plus minus and minus. Clear? Because alpha 3 I have written as minus alpha 2. Clear? Got it? Everybody followed it. Now what it's a linear combination with a minus sign here. Clear? Now if you act Sx total on this very state, that will also give you 0. So if you act like this thing, Sy total on this state, okay, this psi with what? Okay, Sx total equal to 0, Sz total equal to 0 on this very state, that will also give you. So that means you are having all the components of the angular momentum of this very state what? 0. So in other words, it's actually an isotropic state. So when you are having an angular momentum, let's say you are having L equal to 0 state, the orbital angular momentum L equal to 0, that you call S orbital, is it? So is that isotropic? Because that's a spherically symmetric, clear? So then you are having, so this kind of state, which is isotropic in nature, or we call it as a rotational invariant kind of state, so this we call as a singlet state. So this is a singlet state constructed out of what? So we call this as a singlet state constructed out of 2 particles. So you can be having a singlet state for more than 2 particles as well. Got it? Which is carry all the projections of this angular momentum to be 0. So samajh aaya? Everybody got it? Okay, good. So I will take a few more minutes. So let's wait. So maybe we can take Wahid's class today. Can we take? Huh? So I want to finish something more. So because what I have done, this is these are trivial exercises. Okay. So if you have any different, I will provide you notes. Okay. So on Friday, somebody should come to me. So I'll give notes of this very unit. You will not be able to find this in books. Okay, so let me give a home assignment for you people. So do this thing. This is an important example. Okay, so first let me explain the problem. Now let's say if you are having 2 spins. Okay, so you can think classically. You can think a spin degree of freedom giving you the dipole moment. A magnetic, okay, a dipole moment that is proportional to a spin degree of freedom. Clear? So let's say if you are having 2 spin half particles. Okay, so let me first write. So you are having a magnetic dipole moment proportional to the spin operand, clear? Or the spin angular momentum. Okay, so if you construct the dipole moment due to this spin angular, you can be having a dipole moment due to orbital angular momentum as well. I am not considering that, clear? Now you are having 2 spin half particles, they are carrying now dipole moment, clear? Okay, so let's try to interact these dipoles. So what you will be getting? A dipole-dipole interaction, clear? So how you write that? So you write, okay, for spin half particles, for 2 spin half particles, I can write dipole-dipole interaction like this. Okay. So dipoles due to the this spin angular momentum. Let's write that as the Hamiltonian. That can be proportional to actually this, okay, dipole moment of the spin 1 dot of dipole moment of the spin 2. Clear? Is that true? Can I write like this? Is this a dipole interaction? Huh? Is this? You sure? Huh? Okay. So now what is mu1? It's proportional to S1. What is mu 2? Proportional to S2. So or I can write this S proportional to something S1 dot of S2. So let me put a vector here, or you can put a operator kind of thing. Okay. So this is a interaction between two spin degrees of freedom. Clear? So if you are having two spin half particles, now let's make them interactive. So you can put the interaction as this kind of thing. So I will write this proportionality constant to be J. S1 dot S2. This J can be negative as well as positive. It will simply describe you what kind of interaction you are having. Okay. So whether it's a repulsive kind of thing, whether it's an attractive kind of thing. Clear? So much ever? Okay, let's forget about the sign of J for the timing whatsoever it is. So what you are having here essentially S1 dot S2. Now let's write it. This S1 dot S2. So you can write this S1 dot S2 as like this thing. SX1, okay, SX2. Can you write? Then SY1, SY2 plus SZ1, SZ. Can you write it this way? Just a dot product of the two vectors having the components Sx, Sy and Sz. Clear? So much essence. Okay, so if you see this thing, now look here. So since Sx1 is an operator in the Hilbert space of what? Particle 1, and Sx2 is where? In for the particle 2. So this is essentially like this thing. Sx1 tensor Sx2 plus Sy tensor Sy2 plus Sz1 tensor Sz. Okay, now what is Sx? So you can write it as H cross by 2 sigma x, H cross by 2 sigma x. So it will be something H cross square by 4 like this. Sigma x1, sigma x2 plus sigma y1, sigma y2 plus sigma z1, sigma z. Clear? Now you know the matrices sigma x, sigma y, sigma z. You know that? So Pauli spin matrices you know. Now write the matrix. What will be the dimensions of this matrix now? 4 by 4. Because this is 2 by 2 matrix, this is 2 by 2 matrix. Now look here, if you consider this product as a simple multiplication of the matrices, this is a 2 by 2 matrix, this is a 2 by 2 matrix, what will be the resultant there? Only a 2 by 2 matrix. Clear? We have just seen a 2 particle Hilbert space for 2 spin half particles are 4 dimensional. And the Hamiltonian should be what? A 4 by 4 matrix. Clear? समझ आओ? Got it? Okay, because the energy eigenstates have to be what? A 4 column vectors. समझ आओ? Okay, so that's why you need to put a tensor product here to get rid of the confusion whether this simple product or a tensor product or a direct product. Forget about it. Okay, so I will write this H. So this I have shown now. So it will be J H cross square by 4. It will be something like 1 0 0 0 0 minus 1 2 0 0 2 minus 1 0 0 0 0 1. So this is the Hamiltonian you will arrive at. Clear? So समझ आवा? So what is now the assignment? Assignment is find the eigenstates and the eigenvalues of this H. Clear? So समझ आवा? Find eigenstates and eigenvalues. Okay? So you will see you will be getting like this thing plus plus, but in the that column form. So you have to identify it. So समझ आवा? So and so on. So these will be actually the vectors which will give you the eigenvalues and eigenstates. Clear? समझ आवा? Any problem or any question? So I'll be taking away this class today. So if you are any